In this video, I will talk about seemingly unrelated regressions, commonly known as SUR model. So first I will provide a few examples of systems of equations. Then I will specify the SUR model. We will talk about how SUR is estimated, and finally we will talk about properties of the SUR model. So here are a few examples that I have of systems of equations. The first one is the most popular one, where we have demand system for food items for individuals. So for example, we can talk about the demand for different types of products such as fruits, veggies, meat, dairy, and so on, and how which factors affect those demand for these products. And what happens here is that when I consume meat and veggies, they may be related for me, but my choices are unrelated to your choices. So therefore we have regressions that are correlated amongst my choices, but not correlated between mine and yours. The next example that we have here is expenditure system for several different types of expenditures. For example, you can think about how we spend our money, how much goes for housing, for auto, for education, for food, and so on. And these expenditures, again, would be related for a given individual, but not related across individuals. And the final example is the demand and supply models, where we have quantity and prices and how they relate to each other. So in a system of equations that's linear, we would have multiple equations instead of one equation. And I wanted to give you the difference between simultaneous equation models, and I described those simultaneous equation models in another video when I talk about instrumental variables. They contain both endogenous and exogenous regressors, and typically if a regressor is endogenous, it means it shows up somewhere else in another equation as a dependent variable. So I will not talk about these models in this video. I will concentrate on the second type, which is the seemingly unrelated regression, and they contain only exogenous regressors. There are no endogenous regressors in this kind of model. So the SUR model is a system of linear equations, and these errors are correlated across equations for a given individuals, but are uncorrelated across individuals. So again, correlation among choices for a given person, but not correlated from one person to the next. So in the model we have J equals from 1 to m linear regression equations for I equals 1 to n individuals. So here we would have yij equals xij prime beta j plus uij. So notice that here now we have these variables listed over I, which is the individuals, and over j, which are the products or decisions or choices that each individual has to make. And if you stack all of these observations across individuals, then you would have just dropping the I subscript here. And this model that we see here, it could be also written out like that, because J here, the subscript, varies from 1 to m. So what we're doing here, we have, again, from 1 to m equations, J equations, m equations, and then we have, these are the independent variables, the coefficients, and the error term. So again, we would concentrate on what happens with the jth equation. So the error terms are assumed to have zero mean and to be independent across individuals and homoscedastic. And for a given individual, the errors are correlated across equation, which is the expectation of uij, ij prime would be equal to sigma jj prime. So again, you see that you have I repeats here, so that is for the same person, but j and j prime are the two different equations for the same individual. So we want these correlated across equation for the same individual. So more formally, this error term uj would satisfy the following conditions. The first one, we talked about the mean of uj would be equal to 0. The variance of the error term in equation j would be sigma jj, this identity matrix of the dimension n for n people. So sigma jj is again a variance for this of the error term for this equation j. The covariance across equations j and j prime would be sigma j and j prime. So we are correlating this times the identity matrix. And again, here is the real one of the very important points about the SUR model, because this one is not 0. We have covariance across equations for the same individual. And the overall variance covariance matrix would be equal to sigma Kronecker product, the identity matrix. So here's how SUR estimation is done. First, we could estimate an OLS regression, which would yield consistent estimator of beta, but the optimal estimator here is the Gls Estimator. And for the Gls Estimator, we would have x prime, and then here we have this variance covariance matrix that I talked about in the previous slide. So we would have x prime, this variance covariance matrix as x inverse, x prime, again the same expression y. And again, we would have that this variance of beta would be equal to this expression. So we have a little bit more complicated case here in order to consider this covariance that we have across the equations. So how we do the estimation for the SUR model? In the first step, we would estimate each equation by OLS, and then we would save the residuals from the M equations, and that would be equal to uj hat would be equal to yj minus xj beta j hat. So once we form these residuals, then we can calculate this variance covariance matrix based on the residuals that we have. And in the second step of this estimation procedure, we can substitute the sigma hat for sigma in this Gls Estimator. So notice how everything else is the same. We're just substituting this from the first stage equation. So what we mean here is we are correcting those estimates a little bit for the correlation across the equations. So if there's no correlation, if we have basically same variables, no correlation, that would be equivalent to the OLS estimates. But when we have a strong correlation, then those estimates using the SUR estimation procedure would be different, of course. So one thing that we can do also when we're estimating these systems of equations is that we can test cross-equation restrictions and we can impose constraints. So we can test whether coefficients are jointly significantly different from 0. And notice that here we have coefficients beta j and beta j prime equal to 0. So these two are coming from different equations. They're not the coefficients within a given equation, which of course you can do, but they're coming from different equations. And whether these coefficients are significantly different from each other, but not necessarily significantly different than 0. And once we do these tests, we may find that they're not significantly different from each other, so we can impose cross-equation restrictions and then estimate the SUR model. So for example, if we have a demand system and we have how, say, income affects different demand for different product groups, we could say that income probably affects our demand for vegetables the same way as it affects our demand for fruit, but maybe it doesn't affect it in the same way as, say, for some luxury items or group items like eating out or something like that. And so if the effects are, if we want to impose this cross-equation restriction, we can just restrict those parameters to be equal to each other and then estimate the SUR model. So the final thing that I have here is to talk about the properties of the SUR model. This model is used to gain efficiency when the equations are only related through the error term. The parameters in the SUR model would generally vary from equation to equation. And then the regressors may or may not vary from equation to equation depending on the model. Sometimes some variables make sense to be in certain equations but not others. And we would have the SUR estimates would be the same as the equation by equation OLS estimates when we have two conditions. First of all, the errors are uncorrelated across equations, so we would have the sigma, the variance covariance matrix would be diagonal. And second, we have that each of the equations would contain exactly the same set of regressors, so that xj would be equal to xj prime. So that's all I had about the SUR model. So now please join me in watching the video on SUR example and then how to do it with different software. Thank you for watching.